Welcome to physics class by Ambaresh Hugar. And this video, just we explain about the measurement of dielectric constant of a solid by Hopkison's null method. So, measurement of the dielectric constant. We know dielectric constant already. Now we study about the dielectric constant will be measured of a solid or in a solid by the Hopkison's null method, right? So it is a very important methods to measure the dielectric constant of a solid body, right? So already we know that the number of the examples of the solid bodies are considered as the dielectric constant, right? So in this dielectric constant we have to use in the capacitor or we have to use it in the condenser, right? So first in this figure will shows or in this circuit diagram has shows for the measurement of dielectric constant of a solid in a slab. Now first we have to consider as, so this is the electric meter, right? So now mainly you have to consider a solid body, right? So this is the solid, right? So which solid body? The dielectric constant, right? So in this dielectric constant you have to take the, so this is the solid body, means dielectric constant, right? Now when this dielectric constant is placed on the lower plate of the condenser, so this is the condenser C2, right? C2 is one of the condenser. In this condenser having the two plates, one is A and B, upper plate A and lower plate B, right? So the solid body is placed the lower plate on the lower plate in the condenser, right? As well, and the C1 is, it is also one of the condenser. So which condenser? The variable condenser, right? So it is the variable condenser, but it is the constant condenser, right? So in the condenser is considered the cylindrically constituted of the coaxial cylindrical conductors, and now inner cylinder can be slide inside the outer ones, hence the capacity of his condenser can be increased or decreased, means the value of the condenser can be increased or decreased. So by the increasing and decreasing the area of overlap, this is the overlap of the area. If overlap of the area increases or it decreases, then conductor as increases and decreases, right? Now consider, so this is the B is earth. Now it is considered as the battery, right? So this is the battery, you have to consider B. So in this battery is connected to the earth, so the ground, right? So and the next one is we have to consider this is the K1 and K2, right? So in between the K1 and K2 is connected to the electric meters and electrometer, right? So high potential when the key high potential, so we have to take the two batteries or intermediate, the two batteries connected to the ground, right? And this is the electric field, right? So EMF will be applied, right? So in this electrometer is considered the four quadrant A, B, C and D, and this is the needle, right? So when it increasing or decreasing, it will be shows by the deflections of the needle, right? Now when the K1 and K2 are just depressed, K1 and K2 are just depressed, right? So depressed means it will be connected, so in this like, right? So and C1 and C2, both are the capacitor are charged. Now C1 and C2 both are the capacitor are charged, but in the opposite direction, right? So this is connected to the positive terminals of the battery, but this is connected to the negative terminals of the battery. Means C1 C2 is connected to the negative terminals of the battery and C1 is connected to the positive terminals of the battery. So it will be charged equivalent opposite directions, right? If two condenser, so this is the condenser C1 and condenser C2, right? If two condenser are equal capacity, having the equal capacity, they will acquire equal and opposite charges. They will acquire equal and opposite charges, right? If K1 and K2, right? Now if K1 and K2 are just raised, means it will be connected the, so on this like, right? K1 and K2, right? K1 and K2 are raised, then the contact C1 and C2 are connection, C1 and C2 are connection, right? So with the, and now the battery is just broken, just battery is broken. The next, the charge of the capacitor has neutralized, it will be neutralized one another. So deflection of electron, no, where the charge is neutralized, there is no deflection of the electrometer, there is no, it will be, there is no shows in the electrometer, right? This is the obtained by the existing capacitance of the variable capacitor C1, right? It is a capacitor C1, right? So now we have to discuss about the a solid body. So dielectric solid body, we have to measure the dielectric constant, right, by the Hopkins null method. So we have to take the slab. So this is the slab, right? Dielectric slab. The dielectric slab is placed on the, so lower plate on the C2, right? Lower plate on the C2, and it will be capacitor, the distance in between the, so D. So A and B is the distance, will be take the D. Then given dielectric of the thickness, so in this thickness, so this is the thickness, dielectric thickness, so it is the thickness, right? So thickness is indicated or denoted by the small letter t. And next, this increase the capacity of the C2. If increase the capacity of the C2, the previous adjustment of the C1 is kept undisturbed. So C1 has kept the adjustment and undisturbed, and the plate B is moved. Plate B is moved downward until again no deflection. So there is a no deflection, right? So in the electrometer, right? When K1 and K2 are just raised, again you have to K1 and K2 are raised such that C1 and C2 are connected in the electrometer. Now C1 and C2 are connected to the electrometer, right? So we have to derivations, or have to consider what is the constant, the electric constant, right? So first we have to consider x is the distance by which the plate B is moved. How much distance will be plate is moved, that the distance is considered as x. Okay, so now the capacitance of C1 without dielectrics, right? So capacitor C1 now we have to consider as without dielectrics. So then only capacitance of the capacitor C1 is considered, C is equal to epsilon naught A divided by distance D, right? If if A is effective area, so this is the A, epsilon naught is permittivity of the free space, right? Means without dielectric constant, right? But A is effective area of the Gaussian C, effective area of Gaussian capacitor, right? The capacitance of C2 is after introduce the, so which one is after introduce the slab. So what is the capacitance? The capacitance of the capacitance of the slab. So when electrometer shows no deflection, Okay, when electrometer is no deflection, right? So next we have to consider, therefore capacitance of capacitor C is equal to, so we know epsilon naught A divided by D. So means after inside the, or after just inside the slab, then C is equal to epsilon naught A, then so this is the T, means the distance in between the A and B, and x is the, so how much distance will be moved, so that is the x, and T is the thickness, right, into 1 minus 1 divided by K, so it is the constant K. Now we have to calculate the K, dielectric constant. So we know that the capacitance C is equal to epsilon naught A divided by D is equal to, as the same, epsilon naught A, so denominator will be denominator, right? So now epsilon naught A and epsilon naught A, so as it will be cancelled, because the epsilon naught A is comes to in the right side, so denominator, so numerator and denominator has cancelled. So therefore 1 divided by D and 1 divided by D plus x minus T into 1 minus 1 divided by K, right? In total, the both side of the terminals of the, just we have to take the reciprocal, right? So then we will getting the D. So D is the distance, right? Distance is equal to distance plus x minus T into 1 minus 1 divided by K, right? So if we getting the D is to the right side, then we will take the D and D has cancelled, right? And remaining only we have to take the x minus T into 1 minus 1 divided by K. So I have to take the x minus T into 1 minus 1 divided by K is equal to the 0, right? So now we should be find out now, so this is the K, right? Now x is equal to, we can take the x is equal to the, so minus, it will be converted in the plus, right? T into 1 divided by T into, so you have to take the T, x T minus 1 divided by K, then finally you will getting the, so value of the dielectric constant K is equal to thickness divided by thickness minus x, means the value of the dielectric constant is depends on the thickness and distance moved, right? Where the thickness is increases and dielectric constant is also increases, right? So x, so it will be, so difference of the thickness minus x, right? Then totally in this equations you have to consider as the dielectric constant of a solid, right? So we have to using in this equation, so we have to calculate the dielectric constant. So in this equations is given by the method of the Hopkins null. Null method means, so there is no deflection, right? So this is the easiest method to find the dielectric constant of a solid body, right? And more thing, right? So I have to consider the two capacitor C1 and C2, right? So it is a variable, okay na? So which used for only the adjustment of the capacitor for the C2, right? So in this total, the method has explained by the a great scientist of the Hopkison's, right? So that we have to consider as Hopkison's null method. Thank you for watching this video.